Okay, we're going to be taking a look at 1.3 evaluating limits analytically. There's a lot of properties here up front. They're pretty intuitive, and so but we'll go through them, give some examples. But we're going to be utilizing these as we go through and solve or evaluate limits algebraically. So let's go ahead and start. Basic limits. What we have first is we have a limit as x approaches c. Now remember, c is just going to be any constant. So a good example of this would be if I had, let's say, the problem, the limit as x approaches 3. And then what b represents is another constant. So let's just say 4, for instance. Okay, so if we had a problem like this, um, graphically, remember what 4 is, our function 4. If you graph this, it's a horizontal line. And so if we go up to 4, and if we were on to graph that, what we have is a horizontal line at 4. So notice no matter what value I choose, whether it's 3 is what I have as my C, or it could be, let's say, 7, what we have is as we approach 3, as x approaches 3, our y value is always going to be 4, no matter if it's 3 or 7. So if it's just a constant, our value is simply the constant. Okay, so that would be our solution for, or our property for the first one here. Taking a look at the second one, says the limit as x approaches c of x. Now x isn't a constant, it's just a variable. And so what we want to do here is we're going to take whatever constant, whatever value we have down here, and then we'll end up replacing that x. And so a good example of this is a limit as x approaches 2 of x is simply, we take this 2 and we do a direct substitution, and so we get 2. Okay, so if you're allowed to do a direct substitution, we want to do that. And so that's going to be what we do when it's just x. Now, that also applies if we're doing things that have exponents. And so if it's x squared or something like that. So again, just to look at one, if we have a limit as x approaches, let's say 3, and we have something like x cubed, okay, so something like this, then all we need to do is we're just going to take that constant, whatever we're approaching, and plug that in. So it's called a direct substitution, and that's always what we want to try first. And so you end up getting 9 times 3, which is 27, so that's our value. So those are the three basic limits that we're going to be looking at, and some of the properties that we're going to look here. Let's assume that the limit of f of x is always going to be L. So no matter what we're approaching, we're just going to call the limit of f L and the limit of g k. So we're just going to utilize those two values to represent those two limits. So the first one's called a scalar multiple. And what it says is this: if I have a limit as x approaches some values, let's say 2, and then what we have is like a coefficient in front of a function. So we have 3 and then something like x squared. Okay, so what we have is we're going to be utilizing number 3, that's the x squared, but what we have is like a constant out in front. And so we don't typically do this, but what this property is saying is that you can almost really take that constant of 3 and move that out in front of the limit. And so it'll look something like this. If it's a constant, remember, it has to be a constant, so a scalar. So if we look at something like this, now we go back to that number 3, and we do a direct substitution, so we get 3 times 4, which is 12, is our value. Now, that's not really how we are going to look at that, but that is sort of what's going on. What we're going to do is always do a direct substitution, and so if we can. And so we do a direct substitution, and we get 12. So that's all it says. Again, fairly intuitive. It just looks really funky as we're looking at these properties. The sum or difference is just simply saying if you have a limit as we're approaching some value, and then you have something like x squared plus x, or something similar to that. What you can do is you're going to take the limit of the first one plus, in this case, the limit of the second one. And so that's what the property is saying. Now, what we'll end up doing, again, is just take here and we'll do a direct substitution. So we'll have 2 squared plus 2. In this case, that would be 6. Okay, so we're always looking to do a direct substitution. So all of these are sort of like that. A product, a quotient, even a power, all of those are simply direct substitutions. But for us to do things in math, we got to be able to have properties. And so that's what this does. This sort of allows us to see the properties that we're going to be utilizing. So here's the strategies for finding limits. And we're going to be taking a look at really the first 2 to start with. And then 3 and 4 we'll end up doing sort of in an additional type of video. Okay, but we're going to take a look at is number one, direct substitution, and number two, simplifying through different strategies. And so the direct substitution is stuff we just sort of mentioned, but if we have a limit and we're approaching any value, so let's say -1, and then up here I have something like 2x squared plus 3x minus 4. Let's say that's the function that I want to evaluate the limit to. So graphically, this would be a parabola from the x squared. And so we'd plug it in. So you can sort of picture it in your mind, a parabola, and we should be meeting. Parabolas are continuous, so we should be meeting somewhere as we get close to -1 from the left and from the right. But the nice thing about doing this algebraically is that what we can do is we can simply take this value, and if possible, can we just do a direct substitution? So in this case, if I plug in -1, nothing's really stopping me from evaluating this at -1. And so that's what I want to do. And so as we look here, what we have is we end up getting 2 times 1 minus 3 in this case. And so what we have is 3 times -1 is -3 or -3 and there. And so we end up getting 2 minus 3 minus 4, which is -5. And so our limit, the value of this limit, what's in blue, is simply -5. So a direct substitution is always what we want to try first. There's just times where the direct substitution doesn't always work. And so just to give you a real quick example of one of those, and then we'll look at some more examples as we get going, is a limit as x approaches 1, and let's say it's x squared minus 1 over x minus 1. Let's say that was our problem. Well, the first thing we always try to do, if we can, is we want to go ahead and try to do a direct substitution. So could I take this 1 and simply plug it in? And when we do this, notice what we get is we get 0 over 0. Now, 0 over 0 is going to tell us two different things in calculus. The first thing right now just means I can simplify it and then do a direct substitution. So I'm going to need to simplify, and then I'll be able to do a direct substitution. Now, eventually, we're going to see 0 over 0, and we're going to think, oh, we're going to L'Hopital that thing. And so right now, that doesn't make a lot of sense. That's not something that we're going to talk about until we get through derivatives kind of thing. So we'll put that on the back burner. But for right now, what we're going to do is we're simply going to do a simplification thing. So if you get 0 over 0, obviously that doesn't work out very well. And so what can we do to get this to where I can use a direct substitution? One of the strategies is factoring. So a good rule of thumb is if you see like a polynomial, so if you look here, what we have is like polynomials on top and bottom. There's a good chance that factoring would come into play. Complex fractions would be another one. We may look at rationalization as well today. We'll see what kind of time we have. And then definitely the trig stuff will be obvious because you have trig things. So you sort of want to look at it and have a sort of an idea of, okay, do I have fractions inside of fractions? It's probably complex. I need to simplify. Is it polynomials on top of polynomials? Then it's probably going to be a factoring process. Do I see radicals? Then it's probably a rationalization. So in this case, we're going to look to factor and see if we can't simplify. So we're going to factor the numerator. And so we'll go ahead and factor it first. And so what we get is x plus 1 times x minus 1. So that's the difference of two squares. And then we have x minus 1 on the bottom. And so what you'll notice here is as we have this, we can actually simplify this rational expression through this vertical cancellation. And so our simplified expression is x plus 1. And so what we now can do is I can rewrite this limit problem as x approaches 1 of my simplified function. Now, if you take a look at this, do you notice that nothing is stopping me from now doing a direct substitution? So we simplified this expression so that I can get to a direct substitution and find my limit. If you remember from pre-calc, what we have going on here is this is actually a line with a hole in it. So think graphically, if we have a line with a hole in it, and so the hole ends up being at 1, and specifically at 1, 2, for this problem. And so it'll look something like that graphically. Now think about what we did in the first section when we talked about evaluating limits graphically. We said, well, if we're going to be approaching, let's say, the value of 1, we want to approach it from the left-hand side and from the right-hand side. And we want to say, well, what y value are we arbitrarily getting close to if we're arbitrarily getting close to 1 as an x value? And you'll notice it's 2. Now, will we ever get there? No. there's a hole, there's a discontinuity. So there is no value there, but there is a limit that we approach. And so that's where the value is 2. Rationalizing. Now, the rationalization is interesting. And so we rationalize in pre-calc the denominator a lot. So you're used to that. But also we need to be able to look at something like rationalizing the numerator type of thing. And so let me see if I can give you an example of something like that. And so as we approach, let's say 1 again, and we have the square root of x minus 1 over x minus 1. So let's say this was the problem that was given to you. Well, what's the first thing we always try? Direct substitution. So we do a direct substitution to see what we got going on here. And what we have going on is we end up getting 0 over 0. Now, again, what that's going to tell us is right now it means we can simplify using one of these strategies. Eventually, we're going to say, oh, we're going to L'Hopital this thing. But for right now, let's go ahead and simplify. Now, what gives it away is you can factor this. And so if you look at it and go, oh, I actually can factor the numerator, or the denominator is actually what you're going to be factoring, that would be great. Go ahead and do that. However, what we can also do is we can actually rationalize the numerator. There's a radical in the numerator, and a strategy for simplification could be rationalizing. So we're going to use the conjugate to rationalize this 2-term expression here. And so what we end up doing is whatever you do to the top, you got to do to the bottom. And so we're going to multiply the top and bottom by that conjugate. Now, the best way to do this is don't try to simplify the bottom. Now, first off, the bottom, this whole thing is a quantity, so x minus 1, so keep that in the bubble. So just leave that as a bubble. Don't try to FOIL. You're heading in a direction that you don't want to go. So just leave this expanded out. In other words, okay, so like this. Now, in the numerator, we want to go ahead and FOIL this. And hopefully what you remember about using conjugates is that of FOIL, all we're going to do is FL this. So first and last, the outer and inner are going to cancel each other out. And you can go ahead and FOIL that to verify, but hopefully just go FL. So what we're going to do is the square root of x times the square root of x, which is x, and -1 times +1, which is -1. And so there's my numerator. I'm going to put in a bubble so you can see this a little better. Now, notice if I write it like this, notice the numerator and denominator have something very in common. And that's why I didn't want you to distribute through the bottom, is that we can go ahead now and remove that discontinuity that leaves a 1 on top. Don't forget about the 1. That tends to be sometimes something students have trouble remembering. And so we get something like this. Now let's look at our limit with this more simplified expression and see if we can go to a direct substitution. And so as you look at this, if we take the 1 and we do a direct substitution, it actually gives us a value of 1/2. And so what we have as a solution for this limit is going to be 1/2. So those are the strategies. Now, I didn't show you an example of a complex in right here, but we will as we go through some of these problems, so you can see that. Trig, identities, and those kind of things we'll actually look at as well. Those are a part of the lesson coming up. So let's go ahead and look at some examples here, and I'm going to bust through them really quickly and not talk too much about them. So this would be a good time to pause, work through. Obviously, you can only work through sort of the one at a time, but I'll start revealing these as I go through. So I'll just go ahead and start canceling these off so you can sort of work and see them all. But we're going to look at the first 4 at least first. And these first 4 you're going to see are going to involve really the first thing we always try, which is a direct substitution. So let's look at the first one. If I said, what's the limit as x approaches 0, 4x squared plus 3x? First thing I want to do is I always want to try and do a direct substitution. And as I do that, notice that what you get is 0 plus 0, which is 0. And that's the limit. Okay, pretty nice. The direct substitutions you'll love. Now this one looks like there could be an issue because of x plus 1 on the bottom, but what I'm plugging in is a 1, not a -1. And so direct substitution should work here. And so we end up getting 1 squared plus 1 plus 2 on top, and then we get 1 plus 1 on the bottom. And so what we end up having is we end up having 4 on the top, and we have 2 on the bottom, which is 2. And so the limit for that rational function is going to be 2. Okay, looking at the third one, again, there's a trig thing, but again, we don't use trig identities of what we're going to look at with these limits, unless we can't do a direct substitution. So that's what we want to try to do, is do a direct substitution. And what you'll notice is we can absolutely do a direct substitution. Now, what we got to pull from pre-calc is what in the world is the cosine of pi? And so hopefully you're starting to get used to that, but the cosine curve, if you go off the curves, look like this. And so pi over 2, and then pi is -1. And so what we have is actually the answer is pi times -1, which is the opposite of pi. So use that cosine curve to help you with that. And then remember, if it's over 4, over 6, or over 3, use your reference angles to help you with those special right triangles. Looking at the last one here, again, there could be an issue if x was a 4, but x is not a 4, it's a 1. So there shouldn't be any issues. We'll do a direct substitution. I end up getting -15 on top when I do a direct substitution. I get -3 on the bottom. So that leaves me with a +5 as my limit. So all 4 of those are a direct substitution. Okay. Looking at the next two, let's go 5 and 6. So if we take a look at number 5, the first thing that we obviously want to try to do is a direct substitution. So we want to take this 2 and just try to plug it in. And now when we do that, we get 0 over 0. So this is where, again, in our minds, we need to be thinking, okay, we're not done. We're not over. What I want to do is I want to simplify this, and eventually we'll say L'Hopital. So I'm putting that in your mind because eventually we'll just do that. But for right now, let's just look at simplifying this. And so we look and we see, hopefully what you see is polynomials. So that means factoring could be involved. Okay, so I'm going to go ahead and I'm going to look at factoring the numerator or the denominator or both. And in this case, the numerator is the difference of 2 cubes. And so you got to remember from pre-calc a little bit, or algebra 2, how to factor the difference of 2 cubes. And it goes little bubble, big bubble. That's not really a bubble. Let's try that again. Big bubble. So we got little bubble, big bubble. Then hopefully you remember it goes what? Keep the sign, change the sign, always plus, and then it goes A. Now remember, the A is what cubed. There's our template. So I don't want to take you back to pre-calc too much, but our templates are what cube gives you x cubed, what cube gives you 8. And so what we have is we have our A is x, so it goes A, B. B is what cube gives you 8, which is 2. Then it goes A squared, AB, B squared, which is 4. There's our numerator. And now look at your denominator. I'm going to go ahead and put the bubble around it. And now we look to see if we can simplify. And what you'll notice is we can remove that discontinuity from the problem. And that should allow us to get rid of those zeros that we had on top and bottom and be able to just do a direct substitution. So we use the simplification technique still to get back to that direct substitution. So you end up, in this case, getting 2 squared plus 2 times 2, which is 4. I'm going to go ahead and write that, and another 4. So you have 3 sets of 4, or 3 4s here. And what you get is you don't get 13, you get 12. Okay, and so that's where we're at there. So the limit is 12. If you look at number 6, this is an interesting one. Taking a look at one like this one, seeing the factoring is a little tough. Now you could expand the numerator here and then look to factor after that, and that would be fine. There's nothing wrong with that at all. There would be a GCF, but it'd be great if you guys could see the difference of 2 squares. This is our A, and then 2 squared. So 2 is our B. And so you could do something like this, x minus 2. So A plus B times A minus B. And then that's over x. So my goal is to get to the x. Because now the reason I'm doing this, and I sort of skipped over this, but if you plugged in 0, you end up getting 0 over 0. And so that means, okay, we got to simplify this in some manner. So that means through like factoring. It could be through rationalizing the numerator. It could be complex fractions, or eventually we'll get to the trig stuff. And so in this case, what you'll notice is all of these go away, these 2's, for this first bubble. And so we'll go ahead and cancel those. And so you end up getting x times x minus 4 over x. Don't distribute that x. Because again, our goal here is to simplify and remove the zeros that were creating issues. And that allows us to do that vertically right there. So now what we can do is take the 0, do a direct substitution, and what you'll find is the limit is actually equal to -4 for that one right there. Okay, and so that would be your solution for that limit. Okay, I'm going to go ahead and clear the screen, and that allows us to look at this last one here that we have. Okay. And so here's your rationalizing technique. And so you can see, obviously, I've said that with the wording, but I want you to notice that there's radicals in the numerator. And so factoring isn't really necessarily what should come to our minds. It's not a complex fraction. There's no trig stuff. So hopefully this idea of rationalizing is what comes to our mind. Now, what's the first thing we always try to do, though, whenever we get a limit? And that is a direct substitution. And so what we want to do is we want to look at this and say, what happens if I do a direct substitution? And so if I directly substitute it in, I'd end up getting 0 over 0. Now, what that implies is it says, okay, I can go to work. And so we're going to be able to do some simplification here through different techniques to be able to get it. So we're going to rationalize the numerator by using its conjugate. And so the conjugate is going to be the square root of x plus 1 plus 1. That would be its conjugate. And then we're going to multiply the denominator. Now, again, don't oversimplify, because our goal is to get rid of the x in the denominator, because that's creating a 0 in the denominator. So we want to get rid of it so that we can do a direct substitution. So don't distribute your x through that quantity in the denominator. Leave the x out in front. The numerator, you can anticipate what's going to happen here, hopefully the numerator will get an x out of, so we can do a vertical cancellation. So these are conjugates. So a FOIL, you just got a fl. And so we're going to have x plus 1 is our first of our FOIL. And then you get -1 times +1, which is -1. And so we get something like that. So if you just look at the numerator, which is all I'm going to be concerned with right now, we just get x, which is what we wanted. And then the denominator has the x out in front, and then you've got your square root of x plus 1 plus 1. That allows us then to do a vertical cancellation. And once again, I've seen students do this, so be very careful. Your answer should not be the square root of x plus 1 plus 1. That's not what we're evaluating. So we have a tendency sometimes when we cancel and there's nothing left behind, we sort of lose track of what's going on. Remember, in this case, what's left behind in the numerator is a 1, so it's going to be 1 over that quantity. That should allow me now to take my 0 that we started with and now do a direct substitution all the way over here. My pen will allow me to. And plug that in. And once you plug 0 in, what you end up getting is 1/2 as your evaluation. So 1/2 is our limit for using a rationalization technique. Okay, that's where I'm going to go ahead and pause this video, and I'll pick up another one, and what we'll do is we'll start looking at the special trig limits, but that'll at least get you going on the first part of this lesson when it comes to simplification and evaluation of limits algebraically. And so the strategy is this. Number one, you definitely want to try direct substitution first. If that doesn't work with a direct substitution, you get 0 over 0. That means we should be able to simplify. And the strategies of simplification are by factoring, complex fractions, which again, we'll take a look at as we get going, rationalization, and then eventually we'll look at these special trig limits and see where they come from and how to use those as well. And that will wrap up this lesson for 1.3.